So we are team number one, and our project is City Traffic Simulator. We are Francisco, Jorge Andres, Ángel Cedeño, and Máximo Bautista.
Have you ever wondered the number of cars that transit over your street, how they manage to get to their destination, or how they behave according to the semaphores on the area? Well, wonder no more. Our revolutionary city traffic simulator will help you picture a normal traffic scenario where you will be able to configure the number of cars transiting, the number of semaphores in the area, and even the size of the city. You will be able to observe the paths that the cars use to get to their destination, the directions of the streets, how the cars decrease their speed if they have another car in front of them, and many more details. At the end of the simulation, if you need the specific path followed by the cars, you will be able to display them. All of this by the price of 99 cents. Our architecture is basically, we use this class diagram to guide the way we develop. Go is not an object-oriented language, but we use this as a basis. The main part of the system is the board. The board contains the cells of the map, the cars that are inside the simulation, and the semaphores that affect the behavior of the cars. As we can see, most of the methods are related to the board, as the creation of the board. This one is used for the simulation. The intersections are to manage the behavior of the cars inside the simulation, and many more methods, as well as the semaphore. This one has two states, green and red. It affects the behavior of the car if it can cross the intersection or not.
The basic flow of our program is as follows. First, we input all necessary data, and as we are inputted, we validate if it is correct. If not, we display an error saying that the input data will not work. Then we proceed to create the board and obtain the intersections that will become the new semaphores. After having the semaphore set, we create a communication channel for the threads to exchange information. Then we proceed to create the cars and their go routines. After everything is settled, we start to display the board and the cars moving around. When the cars arrive to a destination, we can decide if we want to display the routes, and if we want, the routes will be displayed. If not, then it's the end of the program.
So for the source code, here we have it. It's basically, we have the types of data. We have the cells, we have the cars, semaphores, and queue elements, which basically act as nodes of a linked list, but they are just elements of the queue pointing to the previous element in the same queue. We have constants for streets and buildings, which are types of cells. We have the directions of the cells, which no direction for building and the direction of the street. We have some global variables, including the random seed, which is created by Unix nanoseconds. And we have the board, the paths, and the cars. So here we have an auxiliary, this will work as an auxiliary function to get the intersections. Basically just calculates where each intersection should go, which will be used here in the main, which follows the flow that we explained earlier. Basically, we grab the flags. If something was to be incorrect, well, we display the error message. We show the splash screen while it loads. We initialize the semaphores. We create channels and whatnot. Here we have the initialized semaphores, which is basically just creating random numbers in case that there are less semaphores than there are intersections. So we would just put the semaphores randomly across the map. And if the number of intersections is the same as semaphores, well, it just places one in every single intersection. So go routines for the threads. It will create an initial state for the semaphore, and it will change states every certain time. We have the initialized cars as functions. which will just basically create the number of cars provided by the user, and it will create a thread for each one of them, and it will just be moving every certain time. And once it arrives at its destination, it will be removed. Which here we just add the car to the board. We remove the car when it arrives at the destination, and we move the car by getting the elements of the path which was previously pre-calculated by a BFS that we will be explaining later. So here we have the get path, which is basically the BFS, but we had to modify it so that there was no history, because history actually affected the way cars got to their destination. Sometimes they wouldn't know how to get there because the history said that they crossed there, but sometimes you need to cross the same place twice to get to a destination. So we removed it, and they can always find the path. It's 100% certain that they will get to their destination. Here we have the get neighbors function, which is basically just a way of knowing which cells are next to another, and depending on the direction of the street, you will append different neighbors which are reachable from that certain street. And here we have the function build, which is basically just a construction of the path so that it can be displayed in a humanly readable form. We just get the queue and convert it into a stack, and we just repop the stack in order. We have the create board function, which will just create a board of n by n. And we have the show splash screen, which is just a splash screen so that the program can load and get the paths with the BFS. We have the display simulation, which is just printing the board over and over again, which is something that Angel will now proceed to explain.
So following with the code, we have the print board where we actually know the direction of the cells, and if it has a car, we display the car. For example, this is left, we display a arrow to the left, and so on. And in the other case, we paint the streets, the lines of the street, left, right, whatever, and the buildings that are squares. So we have, this only is for user interface. So following, we have the printing of the information about the cars, if they arrive at their destination, speed, and yes, only destination and speed. So finally, we have print reports that show us the origin, destination, and the route followed, if it's in the case that we display it. So following with the demo, we can, here in an example, we had a width of 38 cars and 25 semaphores. So we run it, and we have the splash screen. So here we can see the cars and the information about each car. So sometimes we can see some cars take a loop in the intersection because we don't have the visited method that was explained before, but we can see each car actually arrive at their destination. So as we can see, we finish, and we can see each car report. So here is the report that is by each car, where we can see the origin and the destination and the path followed. So this is the demo, and this is what the program does and how it's displayed to the user.
For this project, our key learnings were that we learned how to manage multi-threading in Golang, how to clean the console's output, how to create an architecture document, how to communicate between threads in Golang, and how to display logical data into something human readable.
And well, the point of that code isn't written in stone refers to how we modify the BFS, because we knew that when there was always some way to get to a destination, and the BFS just wasn't finding them because we had a history, so we removed it so that it could even if it took a little longer to load the program.
So thank
Yeah.
you.